Good afternoon, everyone. Today I'm going to talk about our visual interaction framework for improving dimensionality-reduction-based exploratory data analysis. This is a joint work with Marco Cavallo from IBM Research. And in fact, the work was done while I was at IBM Research as well, which has recently changed. Now I'm missing at Columbia and the city. So let's talk about dimensionality reductions. Dimensionality reduction is really one of the few essential generic tools that data scientists can use, analyze, and visualize high-dimensional data sets, the data sets with large number of attributes or features, right? So dimensionality reduction algorithms reduce the number of dimensions while trying to maximally preserve structures in the data, right? The structure is often quantified as correlations, similarities, or distances among pairs of data point instances. For visualization, we generally reduce the number of dimensions to 2 and visualize the result with a scatter plot. Okay? And just a note here, dimensional reduction works best when the inherent dimensionality of your data is lower than what the number of your data attributes suggests. Right. So here's a specific example. We have a data set with 8 numerical socioeconomic indices of 34 OECD member countries. Now we are going to apply a simple linear dimensionality reduction and obtain two-dimensional representation and visualize the result with a scatter plot. Okay. And this, without any data labels, it is difficult to really interpret what's going on. Let's show some data labels. Let's not forget the favorite country of Donald Trump. That's that. All right. Now Norway is there. So let's make a few observations there. So there is a cluster of Western countries, mostly European countries with US and Canada. And we see surrounding that cluster is Turkey, countries like Turkey, Mexico, and Portugal. So we see Korea and Japan together, a little bit separate from other industrial countries. Right? So after this initial observation, essentially a static inspection of the scatter plot, really if you want to go beyond and beyond your analysis, the existing really tools or techniques could become limited, right? But we would like to ask, types of questions like this. Why is Portugal there? Like, why is Portugal far from other European countries? And what kind of attribute change that we need to bring Portugal near European countries, right? If I increase the student skills value for Turkey, for example, right, would that bring Turkey closer to the cluster of Western countries, right? Why are Korea and Japan are different from other industrial countries? What do exits mean here, actually? Right? So based on motivate these questions, we propose an interaction framework with 2 interactions. The first one is forward projection. The idea is that the interaction should enable user to change the input and dynamically observe how the output changes. So we are changing the input of the model, in this case dimensionality reduction, and see how the model output changes. All right? The second interaction is backward projection. In this case, we would like to enable user to change or express a desired outcome of the model and see how the input needs to change or needs to be synthesized so that model generates the output. Okay. So we take this framework and apply it to PCA and autoencoder-based dimensionality reductions. So the rest of the talk will be about examples. Okay. So forward projection, in this case PCA. Let me go and show you. So you already know the, all right, is this going to be? All right. All right, let me change actually. See, We have the PCA output of the data set I just showed you. So we have Korea, Portugal, Turkey here, your cluster of mostly European countries, along with US and Canada. So let's click on Turkey, right? So the basic forward projection interaction is that. So I would like to be able to change the attributes of Turkey. Let's say student skills. I want to increase the value, for example, and see how the output changes, right? So I'm just increasing. In this case, it turns out that increasing the student skills value for Turkey doesn't get Turkey closer to European Union or European countries. Let's play with another attribute. Let's say, all right, we don't want to do that. All right, let's increase the educational attainment. This is another attribute. It seems that is the major feature that affects the position of Turkey with respect to other European countries, right? And the speed at which this forward projection changes the model output also gives us a clue about how important the feature is. Let's say, look at the feature life satisfaction, right? I'm changing the value of life satisfaction, right? Although the change is quite significant, the position of Turkey or the output of the dimensionality reduction doesn't change. So a quick take home here is that feature is not significant in determining the position of Turkey or the output of the dimensionality reduction. All right. So this is the basic idea of forward projection. You change the input and see how the output changes. Of course, in order to do this dynamically, you need to avoid recomputing dimensionality reductions. For that, we use what's the technique called out-of-sample extrapolation. So details are in the paper. So with forward projections, it's nice to experiment with attribute values, but it's also nicer to have some guides, right? Instead of trying or enumerating all the future values to see how their change affects the output, you might want to see them in advance, how they look like, how these forward projection paths look like. Right? So I'm going to show that how that's going to work. So in this case, right, I'm going to, all right, we introduce a visualization called prolines. Prolines basically tells you, the direction of change for a given attribute, right? For linear techniques, they are going to be lines, straight lines. So for Turkey, for example, I didn't really, without even trying or experimented with the future values, I could easily see that, okay, if I increase educational attainment, this is the direction of change. The color encodes the direction of change as well, increasing or decreasing. So let me look at another example here. We use also these prolines, what we call prolines, to encode basic statistical descriptors, such as mean value and, mean value and standard deviation, right? So for UK, for example, or Luxembourg, the student skills is, we can easily see that below the average of the sample data. Okay. So a little bit more detail on how we compute prolines. We go for each attribute. We regularly sample the domain of the attribute, and then pre-compute the forward projections, right? And then connect those pre-computed forward projection locations along curves, right? So, and then we take this opportunity to encode basic statistical summaries about attributes along those lines. Okay. We already showed the demo for prolines. So PCA is one of the most popular linear dimensionality reduction techniques. We also want to apply the framework to a nonlinear dimensionality reduction technique. In this case, we use autoencoder. Autoencoders are neural network models, right? Deep autoencoders with nonlinear activation functions can learn nonlinear mappings between high-dimensional data and their low-dimensional representations. Right? So for training our autoencoder models, we use 3 different data sets. Okay? So I'm going to show you forward projection interaction for autoencoder. Okay, let me see. So in this case, I'm using the MNIST data set. And let's look at a sample. We used 200 samples from the MNIST data set. Let's look at the scatter plot here. We see that there is some variation for zeros, how people type zeros, or there's some variation for ones, not so much for 6, for example, right? So in this case, our data is 28 by 28 pixel at each point. That means that you have 784 dimensions, right? So changing a feature value in this case is equivalent to painting or changing the pixel value, right? So in this, when I look at the prolines, it suggests that I can go and increase that pixel value. Well, let's make sure this is 2. If I go and increase this pixel value here, paint here, it's going to increase, right? Let's try to turn this 7 into 9, right? And it goes closer to 9s. Right. Let's go. So I saw a 4 here among all zeros. Let's send it back to its original members over there. So I'm going to go and delete the second line along that 4, and it goes to 4s. Okay. So the idea is that I'm changing the input and dynamically see how the output changes. In this case, the model again is autoencoder-based dimensionality-reduction. Backward projection, a complementary approach. So we change the input, see how the output changes. Now we are going to change the output, see how the input needs to be generated or updated so that desired output is satisfied, right? Let's see. We are going to look at all those cases. This is PCA case. Right. In this case, answering questions like, what are the attribute changes that I need to bring Portugal closer to the cluster of European countries is very easy. I'm going to pick up Portugal and direct towards other European countries there. So when I look at the data change, it seems that Portugal needs to increase all the index values except working long hours, right? So the same is true for Turkey, right? You can do that too. And one of the nice things about backward projections is you can go and experiment in this space, right? So I can take this output and go and explore the corners of the space. So I can see that this right-hand corner is not a nice place to be for a country, right? All right. So one of the things about dimensionality reductions or any model-based data analysis, the mapping is not one-to-one, obviously. So when you express a desired output, there are more than one input changes that satisfy that desired output change. So that means that the function is not one-to-one. We need to insert or express constraints that we can do in our case. So what it means that I can go and set equality constraints. I can say, all right, so don't change student skills. This is equality constraint and educational attainment. And I still go and perform backward projections. Okay. In addition to equality constraints, we can have inequality constraints as well. For example, I can go and say, for Portugal, I want this index value to be, if I can select, less than some value, this is 510, and then I can go and select life satisfaction to be some other, right? Let's see. I want to take, let's play with the more interesting one. All right, this is working long hours. All right, so as we set inequality constraints, we have a visualization. It's called feasibility map. It shows you where the constraints are satisfied and not satisfied. In gray regions, it's not satisfied. And when you move the node with the backward projection, the color changes, and the node moves back to the last feasible region. All right. So this, having constraints has a couple of advantages. You make the job of underlying optimization easier first, but also you can run what-if scenarios with when you have, even if you don't have an underlying optimization problem. Let's look at the way that we create feasibility maps is very easy. We sample the output domain on a regular grid and evaluate the constraint at each grid location, and then visualize the result, the grid itself, with a grayscale map. Okay. Now, backward projection with autoencoder is relatively simple. I'm going to just show that quickly, and we are going to be done. All right. So, so here I can pick, end of nodes here. I can go, move the node anywhere in the output domain, and see how the input needs to be changed, right? And in the case of autoencoder, this is relatively easy because autoencoders learn both forward and backward mappings when they learn dimensionality reductions. All right, so I'm going to start with discussion points. Thank you.
Thank you, Ben Schneiderman, University of Maryland. You provide some provocative examples, but I have to say I still unconvinced that the goal of reducing dimension in a single 2D presentation is the way to understand high-dimensional data. So there are two alternative strategies I would like you to comment on. Your OECD case, a simple one, had only 8 dimensions, which means you only need 28 pairwise scattergrams to see all the data without losing any information. And that would reveal clusters, outliers, gaps, distributions in a more powerful way. So that's the first way. What do you think about an array or a scatterplot matrix?
Yeah, I mean, again, there's the data set itself is basic enough to carry our idea over. For small data sets.
Sure, but that's what you were showing. And I think, even larger, I think, with up to about 150 dimensions, you can still do the scatterplot matrix strategy.
Yeah,
all right.
You can, when you have, think about genomic data sets or gen expressions.
Right, all right.
So you have,
but then your methods would fall apart as well, I think. You wouldn't be able to have prolines for 150 dimensions.
But you can sample, actually, we talked about that.
All right. The second possibility is hierarchical clustering, agglomerative clustering, and dendrogram analyses to be able to show that. It seems much more powerful to reveal features in high-dimensional space.
Yeah, it's just one, but it doesn't change the fact that people use dimensionality reductions to create scatterplot visualization.
They shouldn't. They're dangerous.
Well, maybe. So the idea is that you can use this kind of framework to get some sense of what's going on.
I agree. It's an interesting idea, but I think it only supports what I consider a dangerous approach to visualization.
I would disagree respectfully, but
I understand.
The idea is not just limited to dimensional reductions, right? Think about any model-based analysis. Right? So how are you if you have a black box model, how are you gonna get some dynamic sense of the model? Right? You don't have access to internals of the model, right? And you want to use the model to analyze data or to something else. So we're looking into actually deep learning models as well.
All right.
Where people use
I think there's a good discussion to consider alternatives.
Very quick question.
So this kind of follows on from the previous question, and that is you've got a two-dimensional plot in which you're showing to the user something that looks like similarity. And when you adjust certain variables, you can bring certain countries closer together in that similarity space. But the problem is you've got a multi-dimensional space and you've collapsed it. So along some of these axes, the countries may still be vastly dissimilar. And if you had a scatter matrix plot, then you would...
But the underlying, so I suggest you take a look at the paper, the underlying formation goes back to the high dimensional space. Solve the problem in the high dimensional space.
Yeah, it's what you've got to watch you don't mislead the viewer. I think is the main thing in these.
Well, in fact, this is just an exploratory data analysis.